Next, we want to become familiar with the central limit theorem, one of the most powerful and famous theorems in mathematics, and how to apply it. And there are many applications for that. And so the basic idea is this. When samples are repeatedly taken, the mean of each chosen sample is itself a random variable with the following properties. So here you have all the distribution of the sample mean. So you have mean or samples of size, let's say 10, and take 1,000 of those or 20 of those. And so the distribution of the sample means will be equal to the population mean, and with the following predictable characteristics. So here's the mean, and so the sample, the population mean, and so the sample mean will be, well, so now I got a little bit ahead of myself. So the distribution of the sample means will be normally distributed. So in other words, it'll look like this, okay? And the mean of the sample means, is equal to the population mean, is equal to the population mean. In other words, mu sub x bar, the sample means, is equal to mu, the population mean. Okay? And the standard deviation of the sample means is smaller than this population standard deviation. Okay? So the standard deviation of the sample means is the population standard deviation divided by the square root of the sample size. So the standard deviation of the sample means is the population standard deviation is the population standard deviation divided by the square root of the sample size, right? The sample size n. So in other words, the standard deviation of the sample means is equal to the population standard deviation divided by the square root of n. So this is often referred to as the standard error, of the mean. If all of this sounds a little mysterious, I cannot really blame you, but I will also later on refer you to a video from the Khan Academy, and that makes it very visual and very clear as to what's going on here. So as I mentioned in the beginning, the central limit theorem is very powerful in many ways. And one of the key observations is that even when the parent population is not normally distributed, not even close, as the sample size increases, the sampling distribution of sample means, again, approaches the normal distribution. Okay, so that is the key observation about the central limit theorem. You have any kind of distribution, if you take enough samples and compute their means, then they will approach a normal distribution. So if the parent population is known to be normally distributed, use a sample size of any size. So n, any size. Because then we just talk about a normally distributed population. Okay? But if the parent population is not normally distributed, then use sample size of n greater than or equal to 30. N greater than or equal to 30. In other words, if we use sample sizes of n greater than or equal to 30, it doesn't matter if the parent population is normally distributed or not. We convert the sample mean to a standardized normal distribution in the following way. We compute the z-score as follows. Z equals the sample mean minus the population mean divided by the standard deviation, population standard deviation, divided by the square root of n, the sample size. That's how we convert this into a standard z-score. So we say that x bar is normally distributed with the mean of the population mean and the standard deviation of the population standard deviation divided by the square root of n. So let's look at an example here. Assume male weights follow a normal distribution with a mean of 182.9 pounds and a standard deviation of 40.8 pounds. Describe and draw the distribution of this parent population. X is the individual weight of a randomly selected man. So then X is normally distributed because that's the statement here, with a mean equal to the population mean of 182.9, and the standard deviation would be 40.8. 40.8. And so that does not change, because we are told we have a normal distribution. So here is our horizontal line. Let me make it a straight line for you. And here's our distribution. With a mean of 182.9 and the standard deviation and that's equal to 40.8. Okay? So one standard deviation. Now, the next question is this. A random sample of 16 such men is selected. Describe and draw the sampling distribution of the mean weight for the sample. Again, X bar is the average weight per person for the sample of 16 men. So then X bar is normally distributed. With a mean of 182.9, but the standard deviation is equal to, well, the sample standard deviation is equal to 40.8 divided by the square root of 16. So that would be equal to 10.2. So 10.2. And so now our distribution looks a little bit different. And as you remember from the initial statement that when we have to look at the standard deviation, where the population is not necessarily uniformly distributed. So here's our 182.9 mean, but now our standard deviation of the sample means is equal to 10.2. 10.2 and not 40.8 as before. Okay, so that's one of the differences here. The next example is about elevator weight limits, and we assume that male weights follow the normal distribution described above with a mean of 182.9 pounds and a standard deviation of 40.8 pounds. Suppose an elevator has a maximum capacity of 16 passengers with a total weight of 2,500 pounds. This weight limit equates to an average per person weight of 2,500 divided by 16, or 156.25 pounds per person. So now the question is, find the probability that one randomly selected male has a weight greater than 156.25 pounds. So again, the weight of randomly selected men, that's equal to X, and X is normally distributed, with a mean of 182.9, and a standard deviation of 40.8. So using technology to find the probability that X, that the weight is greater than 156.25 pounds, is simply equal to 0.74318. So in other words, there's about a 74.3% probability that a randomly selected male selected male will weigh more than 156.25 pounds. So in other words, this probability is 0.74318. 156.25 pounds. Let's look at the next part here. Here it says find the probability that a sample of 16 males have a mean weight greater than 156.25 pounds, which puts the total weight at 2,500 pounds, exceeding the maximum capacity. So here, the mean, the average weight per person for the sample of 16 men, and so that is normally distributed. The sample means are normally distributed. And the mean, of course, is the population mean of 182.9. And the sample standard deviation is what we had up here before, is 40.8. In other words, that's sigma divided by the square root of n divided by 16, and it's equal to 10.2. So with these two inputs, and when we use technology for the mean as 182.9 and the sample standard deviation as 10.2, then we find that this is 9.999.9925. In other words, there's a 99.6% probability that the sample of 16 men would have a mean weight of 156.25 pounds or more. So that is with technology, and it's pretty simple. But what if you don't have technology? Well, you can compute the corresponding z-score as shown above. So that z-score would equal the sample mean minus the population mean divided by sigma by the square root of n. So that would be 156.25 minus 182.9 divided by 40.8 divided by the square root of 16, and that is equal to minus 2.61. So when you look at a distribution like that, so here we are, minus 2.61 is here. So that would be on this one here, that would be less. So then what's greater here, this part here, would be 1 minus the area. And the area corresponding to minus 2.61 is, so the probability corresponding to this z-score, this little area here, is 0.0045. So 1 minus 0.0045 is equal to 0.9955. The same result that you got from the technology. Okay? So we find the corresponding z-score, we find the area, 0.0045. We subtract that from 1 because we're interested in this area here. And what's the probability? It's greater than this value here. And we get the same answer. What we can say in conclusion about the last part here is that if the elevator is filled to capacity with men, there's a very strong chance that the safe weight capacity of 2,500 pounds will be exceeded. So in other words, it's a real safety issue. Let's look at an oil change example. Suppose that the mean time for an oil change at a 10-minute oil change job is 11.4 minutes, with a standard deviation of 3.2 minutes. Part A asks, if a random sample of n equals 35 oil changes is selected, describe the sampling distribution of the sample mean. So our random variable x bar is the mean oil change time, mean oil change time, for the 35 selected ones, for the 35 selected. Now the mean, of course, is equal to 11 point, x is normally distributed. X bar is normally distributed, with a mean of 11.4 minutes. Now the standard deviation we need to compute, because the standard deviation for the sample means is equal to the standard deviation sigma divided by the square root of n. So that is equal to 3.2 divided by the square root of 35. 35. And that's equal to 0.5409. So that is 0.5409. So now we're asking so that is a sampling distribution. Now the next part is, if a random sample of n equals 35 oil changes is selected, what is the probability that the mean oil change time is less than 11 minutes? Again, so our sample mean is a mean oil change time, for the 35 selected ones. And again, it is normally distributed with a mean of 11.4. And as we just determined in the previous part, the sample mean standard deviation is 0.5409. So let's draw a graph so that we can better understand what we are computing here. So here's our distribution with a mean of 11.4 minutes. So here's our x-axis, and the unit of measure is minutes. And so here's 11 minutes. 11 minutes. And the question is, what is this area here? What is the probability for this particular area? So if we use technology, we ask, what is the probability of x being less than 11 minutes, given the mean being 11.4 and the standard deviation is 0.5409, and that turns out to be 0.2298, or about 23%. Probability that an oil change at the sample of 35 selected oil changes. We'll have a mean oil change time. That is 11. It's less than 11 minutes. That is less than 11 minutes. So, and here's what you can do when you don't have technology. You can compute the corresponding z-score. So z would be 11, our data value, minus the population mean of 11.4. Again, this is our sample mean for all the samples, divided by 0.5409, 5409, and that is equal to minus 0.7395. And when you look at the table, minus 0.7395, 0.7395, so we have 0.7123, 0.34, so that is about 22.96. So it's not quite the same, but again, this is just a table, so 0.2296 when we use the table, but again, that is not quite accurate. So the technology of 0.2298 is probably more accurate, but still, in terms of percentages, it's still about 23% when we round it up. So let's review and summarize what we have learned so far. Number one, the mean of a sampling distribution is equal to the mean of the parent population. Parent population is equal to the mean of the parent population. In other words, the population from which the samples are drawn. Population. Okay? And then the standard deviation of the sampling distribution is equal to the standard deviation of the parent population divided by the square root of n. And the central limit theorem says the shape of the distribution of sample means becomes approximately normal, as the sample size n increases, as the sample size increases, sample size n, increases, and that means n, equal to 30 or more. Even if the parent population, is not normally distributed. And that is a great insight from the central limit theorem. Okay? Okay. In summary then, if the parent population is normally distributed, that the sample means will be normally distributed for sample size n equals, well, any size. And if the parent population is not normally distributed, the sample means will be normally distributed for sample sizes n greater than or equal to 30. Let's look at a couple more examples. One of them is reach distance. The overhead reach distance of adult women are normally distributed with a mean of 200 centimeters and a standard deviation of 12.5 centimeters. So let's illustrate it with a graph. So here's the reach distance. And where's the reach distance important? Well, when you go in an airplane and you want to reach your overhead bin. So that would be important thing to do to be able to reach your overhead bin. And so here's the distribution we are told is normally distributed. And so with a mean of 200 centimeters, so our x-axis is in centimeters. And so the question is, find the probability that an individual distance is greater than 205 centimeters. So 205 is here. So we are interested in the probability, it means the area under the curve, to the right of 205. So that would be this one here. So our random variable is x, the reach distance. So we know that x is normally distributed with a mean of 200 centimeters and a standard deviation of 12.5 centimeters. 12.5 centimeters. So in other words, what is the probability that x is greater than 205? Using technology, with this information, the mean of 200 and a standard deviation of 12.5, then we find that that's equal to 0.3446. So about 35% of women have that kind of reach distance. That's really what it says. What if you don't have technology? You can compute the corresponding z-score of 205, the sample mean, minus the population mean of 200, divided by a standard deviation of 12.5, and that is equal to 0.4. And so now you look at the table, and 0.4, the corresponding area, is 0.6554. Now that is the area to the left. That is 0.6554. So we need to subtract 1 minus 0.6554. So this area here is 0.6554 to get this area here. And when we do that, we find that's equal to 0.3446, the same as the answer that we got with technology. So in other words, this is 0.3446. That's the area we want. That's the probability we want. The next question deals with the probability that the mean reach distance for 25 randomly selected adult women is greater than 205 centimeters. So the random variable here is the mean reach of mean reach distance. Reach distance for the 25 selected, or the 25 selected. And the distribution x bar is normal, it's normally distributed. And its mean is equal to the population mean of 200. But the sample mean standard deviation we compute as follows. It's equal to the population standard deviation by the square root of n, the sample size. So that's equal to 12.5 divided by 25, and that's equal to 2.5. So that's equal to 2.5. Now when we draw a graph here, our distribution is going to look like this. It's going to be a little bit narrower because the standard deviation is less. Remember the standard deviation before, when we didn't look at the sample just at a single person, it was 12.5. Now it's 2.5, so it's narrower for sure. So let's draw in the important information. Here's our mean of 200, and here's 205. And so what we want to look at here is, what is this area here? What is this probability? Okay. So when we look at the probability using technology of x being greater than 205 centimeters with mean of 200 and a standard deviation of 2.5, then we find it's equal to 0.2275. I mean, 0.02275. 0.02275. So that is the area here, 0.02275. That's like 2.3% or so. And if you don't have technology, you compute the corresponding z-score. So our data value is 205 minus the population mean of 200. And now we divide by the sample standard deviation of 2.5, and that's equal to 2. 5 divided by 2.5 is 2. And now when we look at the z-score table, that is 0.9772. So in other words, this area here, when we use technology, is 0.9772. So to find out what the area is that we are really interested in, we have to subtract from 1 this area, 0.9772, and that's equal to 0.02275 or actually 0.8 when you round that up. So in other words, rounding it will give you the same results. The last question is, why can the normal distribution be used in part B even though the sample size does not exceed 30? Well, that is because the problem statement originally says that the overhead reach distance of adult women are normally distributed. So here it is, it's normally distributed. And in that case, that works for any sample size. Because overhead reach distances are normally distributed. Therefore, the sample size does not have to be sample size, let me just say, can be any size. Can be any size. So in this case, it was 25.